This is the 9-1 video for APC. We're going to calculate the center of mass of objects. And the center of mass of a system of particles is the point that moves as though all the system's mass were concentrated there and all external forces were applied there. Here we have an applet to show us how this works exactly. We're going to have a object move through space. Its center of mass is the black dot right here, and you'll notice that that black dot moves just as if a projectile were moving. If we change where the location of the mass is, let's put the mass more in the center here. Start this off, and you can see it still follows the same projectile, even though the object is traveling a little bit differently. The center of mass will travel as if all the mass was concentrated at one point. If we have a system of particles and we want to solve for the center of mass, we have this equation here. And here's our example of there's an M1 mass here, an M2 mass over here on the right. The center of mass is somewhere in between this red dot. And we want to solve for that center of mass. What we do is we follow this equation here. It's the center of mass along the x-axis is M1 times x1. That's the mass of the first object times the position along the x-axis, plus the second mass times its position along the axis, plus the mass of the third object times its position along the x-axis. Do that for all the particles, and you divide by the net mass. That capital M means the total mass of all those particles. That will give you the position of the center of mass of your particles. You can do this exact same equation for the y-axis and for the z-axis, and that'll give you your x, y, z position. So here's an example. 3 particles of mass 1.2 kilograms, the second mass is 2.5 kilograms, and the third mass is 3.4 kilograms, form an equilateral triangle of edge length 140 centimeters. Where's the center of mass of the system? So I would draw the picture first, set up all the positions, and use the x center of mass, y center of mass equation up above to find out where the actual center of mass is. So here's our picture, and you'll see that M1, M2, and M3 are located here in an equilateral triangle. This right here is actually the answer for this. So what you would do, though, is you would find out the center of mass. You do the center of mass of all 3 particles for the x-axis. And that looks like this. You do M1, the 1.2 kilograms, has its x position at 0. M2, the 2.5 kilograms, has its position out at 140 centimeters. And the 3.4 kilograms, the third mass, you'll notice is at the 70 centimeters. Its x position, I don't care about its y position, I only care about its x position, is at the 70 centimeters. And I add up all 3 masses, do the mathematics here, and you end up with a position of 83 centimeters. Now you're going to do this exact same thing, but for the y-axis. And you just do the different positions. You notice that the first 2 masses have their y-axis value is 0. And then the third mass is up here at 120 centimeters, and its position is 58 centimeters. So we have 83, 58 is our point of our center of mass. Now we want to find the center of mass of not a system of particles, but of a material. And so we have this figure that shows a composite slab with dimensions of 11 centimeters by 2.8 centimeters by 13 centimeters. Half the slab consists of aluminum, and half consists of iron. What are the x-coordinate, y-coordinate, and the z-coordinate of the slab's center of mass? So take a minute here and think about how you would do this and solve this problem. Now you can do this by symmetry. You see if for the x-axis here is along this line, and you know the x-axis is going to be halfway. Just by looking at this picture, you know that it's going to be halfway. It's going to be it'll be right along this line will be the x center of mass. And so that's half of the D3, which is the 13 centimeters, so half of that is 6.5 centimeters. So it's the x-axis is 6.5 centimeters. The y-axis is actually where you're going to have it's going to be offset here. It won't be right in the middle. on the y-axis. And then the z-axis, it actually up and down will be right in the middle as well. So you can, by symmetry, the x and z-axis, you know the answers to that already. It's just the y-axis we have to worry about. So what we show here in part A, that like we said, the x-center mass is 6.5 centimeters. That just means it's that way, negative 6.5. Again, the z-axis is by symmetry. It's the 2.8 divided by 2. It's 1.4 centimeters up. So it's the y-axis we have to worry about. Now, we don't have the mass of any of these, of the iron or the aluminum, but what we will do is use density equals mass over volume to find out what the mass is. And what we'll do is we'll treat this iron as one particle with its center of mass. We'll treat it as a particle right here at this point, right in the center, and the aluminum we're going to treat as a particle right at this point in the center. So it's going to be similar to the previous problems where we had just these point particles. Well, the iron we're going to think of as a point particle, and aluminum we're going to think as a point particle, right at its own particular center of mass. So what we're going to do here is you'll see that we're going to use this equation, y equals my plus my all over the two m's added together. And instead of mass here, we're going to use density times volume. And you'll see that instead of the mass there, we use density times volume, density times volume, density times volume. And in the y position, what we're going to do is we know that D1 has a value of 11 centimeters, and we know that we go halfway over, that's where our position is. 11 centimeters divided by 2. And same thing here, D1, 11 centimeters divided by 2. That's our position right there that we're going to use. It's multiplied by 3 here because really, if you think about this, it's 1.5 times over. You have this 1, you have this mid position, and then this mid position here. And so you have to multiply that 11 halves, that's 6.5 centimeters by 3. So there's 6.5 centimeters, another 6.5 centimeters, another 6.5 centimeters, 3 times over, gets you in the midpoint of that aluminum. You'll also notice that the volumes all cancel out. They all have the same volume, so those volumes go away. This has the same, those V's are all the same. And then you end up with an answer in the y direction of 8.3 centimeters. We'll be doing other similar problems in our problem sets. And if you have a large object like this, all you do is you pretend that it's just a point particle at its own center of mass, and it makes the problem much easier to work with.